Okay, so ready to dive into this year's Nobel Prize in Physics?
Absolutely. Always up for a good deep dive, especially when it comes with a Nobel Prize.
Right. It's especially fascinating this year, because it bridges this gap between what we typically think of as physics and the world of AI.
Yeah, at first glance, physics and AI, they seem like worlds apart, but this year's prize really highlights that deep connection.
Totally. We're diving into the work of John J. Hopfield and Geoffrey E. Hinton, the minds behind artificial neural networks, or ANNs for short. Now, you've probably heard about ANNs in the context of AI, right? But today, we're going to uncover why they're also a physics triumph.
Yeah, and what's so cool about what we're going to get into is how these scientists looked at the complex workings of the human brain and saw not just biology, but a fascinating physics problem waiting to be solved.
Exactly. To really appreciate their work, we need to rewind the clock, like way back to the 1940s.
Wow.
Even before computers as we know them even existed.
Yeah, it's wild to think about it like that, right?
Wild.
But the quest to create intelligent machines, it really did begin back then, even before those room-sized computers were crunching numbers.
I can't even imagine a computer taking up a whole room.
It's hard to fathom now.
It really puts it into perspective. But, how do they even begin to approach this idea of making a machine think, back then?
Well, initially the focus was on, developing programs based on logical rules. It seems like a reasonable starting point, I guess.
Yeah, totally.
But imagine trying to program every single rule for recognizing, let's say, a cat.
It would be impossible.
Yeah.
The fur, the ear shape, the eye color.
Exactly. It quickly became clear that approach was just incredibly complex and computationally demanding.
So true. So while computer scientists were kind of hitting a wall with this programming logic, what was happening over in the world of neuroscience? Weren't they kind of tackling a similar puzzle? How our brains learn and recognize these patterns?
That's right. And this is where things get really interesting. In 1943, neuroscientist Warren McCulloch and logician Walter Pitts, they teamed up and they created this model for how neurons in the brain work together. And their work really had a huge impact on both neuroscience and the development of ANNs.
So they were basically creating the first blueprint for artificial neurons, but drawing inspiration from actual brain cells. That is amazing.
Yeah, it was a breakthrough. They demonstrated that a neuron, it essentially receives signals, weighs their importance, and then it decides whether to fire off a signal of its own. It's a simplification, of course, but it captured that essence of how neurons process information.
So we've got these artificial neurons, right? Inspired by real ones. But how do you connect them into a network that actually functions?
That's the big question, right? And this is where computer science and neuroscience really start to intertwine.
Good.
Two primary network architectures emerged: recurrent networks and feed-forward networks. So imagine recurrent networks like loops, okay, where information can flow back on itself, allowing the network to remember previous input. Think of it like how you might remember a song by repeating the melody in your head.
Oh, like a feedback loop.
Exactly.
And what about feed-forward networks?
Feed-forward networks are a bit more straightforward. Information flows in one direction, kind of like how our senses send information to our brains.
Oh, yeah?
It's a one-way street.
Got it. So did they have much success with either of these early networks?
There were some promising developments for sure. In 1957, Frank Rosenblatt, he developed a feed-forward network called the perceptron.
Okay.
It was designed specifically for image interpretation, and it even had, get this, adjustable connections between its layers of neurons to fine-tune its performance.
Wow, that sounds pretty advanced for the time. So was this a major breakthrough?
Well, while it generated a lot of excitement, the perceptron had its limitations. It excelled at separating data points that could be divided by, a simple line.
Okay.
But it struggled with more complex patterns that weren't what we call linearly separable.
So it could easily tell the difference between a cat and a dog, but maybe not between different breeds of dogs that share, a lot of similar features.
Exactly. And this limitation, it kind of led to some setbacks in funding and research for a while. But little did everyone know that a revolution was brewing and a physicist was about to shake things up.
This is where our deep dive takes us from, the world of computer science into the realm of physics.
Yeah.
Time to talk about John Hopfield.
This is where that physics connection really kicks in, right? John Hopfield, he wasn't a computer scientist.
Okay.
He was a renowned theoretical physicist.
Why?
But he had this knack for spotting patterns in seemingly totally unrelated fields.
So not your typical AI researcher.
Not at all. In the 1970s, he was immersed in the world of, biological processes, electron transfer in molecules and how living systems self-correct.
Gotcha.
Then, bam, 1982, he unveils this groundbreaking model for associative memory.
Oh, yeah?
And get this, it drew inspiration from magnets.
Okay, hold on. Magnets. Is this where my brain starts to melt? How can magnets explain something as complex as, human memory?
It's pretty wild, right?
Yeah.
So Hopfield, he imagined this network of, tiny magnets, each one representing a neuron.
Okay.
And he realized that the way these magnets naturally align themselves in a magnetic field, seeking out their lowest energy state,
Right.
that could actually be used to represent how neurons in a network, they interact and store information.
So instead of programming, specific rules for memory, he let the network kind of find its own stable states based on the connections between these artificial neurons.
Exactly.
It's like the network was learning by finding its most energetically favorable configuration.
Precisely. His model used equations from the world of magnetism, like the Weiss molecular field, to actually describe the behavior of his artificial neural network.
So we're talking actual physics equations being used to model how a network of artificial neurons could learn and remember.
Yeah. And the thing is, it worked. His model, known as the Hopfield network, it acted like an associative memory, capable of correcting errors and completing patterns.
Could you give us an example of how this would work, in practice?
Sure. Imagine you have a jumbled image, say a puzzle with some pieces missing.
Okay.
Hopfield's network could take that incomplete information and, based on those connections between its artificial neurons, it would settle into a state that represents that complete corrected image.
That's incredible. But what was the real significance of Hopfield's work? Was it just about creating this cool model?
Yeah.
Or did it have a deeper impact on the field?
No, it was huge. It wasn't just about the model itself, but for what it proved. He showed that complex computations, they could emerge from a network of relatively simple interconnected units. This was huge. It meant that you didn't need this complicated set of instructions to achieve intelligent behavior,
Oh, yeah.
You could create a system with the right connections and it would essentially organize itself.
So instead of programming intelligence directly, they were creating systems that could learn and adapt, it sounds like the very essence of machine learning as we know it today.
Exactly. Hopfield's work was this fundamental shift in thinking. He bridged that gap between physics and neural networks.
Wow.
Showing that the principles governing the behavior of magnets,
Yeah.
they could also be used to understand how our brains store information.
That's remarkable. It really highlights just how interconnected all these different scientific disciplines really are. But we've got another big name to talk about, Geoffrey Hinton. Where does he fit into all of this?
Oh, Hinton. He took Hopfield's work in a fascinating direction.
Okay.
He introduced this element of probability into the mix.
Probability. So we're talking about the likelihood of something happening. How do you even begin to apply that to an artificial neural network? Are these networks like rolling dice to make decisions?
In a way, yeah. In the mid-1980s, Hinton, along with Terence Sejnowski, they introduced the Boltzmann machine. It's a type of neural network that uses probability and this concept called fictive temperature to determine the state of its artificial neurons.
Okay. Fictive temperature. We need some help with this one. What does temperature have to do with artificial neural networks?
Yeah, it's a bit of an abstract concept, but think of it like this. Imagine the network is hot when it's uncertain, right? And it cools down as it becomes more confident in its decisions. So the Boltzmann machine, it explores all these different possible solutions with the temperature influencing how likely it is to jump between them.
So it's like the network is exploring this landscape of possibilities, and the temperature is kind of controlling how freely it can move around.
Yeah, if the temperature's high, it's more likely to explore, less obvious solutions, while a low temperature keeps it focused on the most likely options.
Gotcha.
Exactly. The Boltzmann machine, it doesn't just settle into that lowest energy state like the Hopfield network.
Right.
It uses probability and this fictive temperature to really find the best solution among a range of possibilities, allowing it to escape getting stuck.
This sounds incredibly complex. Did the Boltzmann machine, live up to its potential?
It was a significant theoretical contribution for sure, but, it did face a challenge.
Okay.
Training a Boltzmann machine, it was computationally expensive.
Yeah, I bet.
Especially with the limited computing power that was available at the time.
Right.
And this made it difficult to apply to, real-world problems.
So a brilliant idea, but not quite ready for prime time.
Yeah.
What happened next? Did Hinton give up on the Boltzmann machine?
Not at all. He continued to refine and develop his ideas, and this led to a modified version called the restricted Boltzmann machine.
Okay.
This streamlined version, it addressed some of those computational challenges of the original Boltzmann machine.
Okay.
It paved the way for even more groundbreaking advancements.
This is where things start to get really exciting. It's no longer just theoretical. We're talking about real-world applications.
Right.
But before we dive into the world of restricted Boltzmann machines and, deep learning, we need to kind of rewind back to the 1980s and revisit those feed-forward networks, because a game-changing algorithm is about to take center stage. Okay, so last time we were talking about, artificial neurons, and we discovered how physicists like John Hopfield, they found inspiration in this, unexpected world of magnets.
Yeah, it really is remarkable how these seemingly, totally different fields can just intersect and create these groundbreaking advancements,
Totally. And we left off with Geoffrey Hinton's, work with Boltzmann machines, remember? Using probability and that fictive temperature to explore this whole world of possibilities.
Yeah, it was a fascinating step forward, but it also came with, some computational challenges.
Right, exactly. And this is where our deep dive takes us to another, pivotal chapter in the story of artificial neural networks, the rise of backpropagation.
Yeah, backpropagation, that really revolutionized the way we train these networks. It made them so much more powerful, so much more capable.
Okay, I have to admit, backpropagation, it sounds kind of intimidating.
It does.
Can you break it down for us? What exactly is it?
Okay, so imagine you're teaching a dog a new trick, right?
Okay.
You give it a command, it responds, and then you offer it a treat if it gets it right, or you gently correct it if it, misses the mark.
So it's all about that feedback, that adjustment.
Exactly. Backpropagation brought that same feedback mechanism to these artificial neural networks. So instead of just feeding information forward, now the network can learn from its mistakes.
Oh, okay.
And it can adjust its connections to, improve its performance.
So it's like the network is constantly refining its understanding, based on the feedback that it's receiving.
Exactly.
Can you give us an example of how that works, in practice?
Sure. Let's say we're training a network to recognize different breeds of dogs, right? So we show it an image of a golden retriever, and it initially misclassifies it as a Labrador.
Happens. Even we humans make mistakes.
Exactly. But here's where the backpropagation comes in. The network, it compares its output, the Labrador classification, with that correct answer, golden retriever, and this difference that's used to adjust the strengths of the connections between its artificial neurons, making it, just slightly more likely to identify a golden retriever correctly the next time.
So it's like fine-tuning a musical instrument, right?
Right.
You're making these tiny adjustments until it produces that sound that you want.
That's a great analogy. And just like a musician, they practice over time. Backpropagation allows that network to learn from its mistakes and become more and more accurate in its predictions.
That makes perfect sense.
Yeah.
But we were talking earlier about how those early feed-forward networks, like the perceptron, they struggled with those more complex problems. How did backpropagation help to kind of overcome that limitation?
That's the key right there. Backpropagation was crucial in the development of these multi-layered networks, with something called, get this, hidden layers.
Hidden layers. Sounds mysterious. What exactly do these hidden layers do?
Think of it like this. Okay, the perceptron with its single layer that was trying to understand a really complex concept with a limited vocabulary. Hidden layers, they add depth and richness to the network's understanding.
Okay, I'm intrigued. Can you elaborate on how that works?
Sure. Let's go back to our dog breed example, right? Imagine that first hidden layer in the network learns to detect these simple features. Edges and lines. Okay.
I'm with you.
Then that next hidden layer might then combine these edges and lines to recognize shapes like circles and squares, which could then represent, say, parts of a dog's face.
So each hidden layer kind of builds upon the previous layer.
Exactly.
Extracting this increasingly complex and abstract information from all that raw data.
Exactly. And then finally, that last hidden layer might combine those shapes into a representation of the dog's face, allowing it to distinguish between that golden retriever and, say, a Labrador, but with much higher accuracy.
So it's like each hidden layer is like adding this new level of understanding, moving from those really simple features to these more complex representations.
Precisely. And this is where Geoffrey Hinton's earlier work on Boltzmann machines comes back into play.
It all connects. I was wondering when we'd circle back to that.
He realized that a modified version of the Boltzmann machine, called the restricted Boltzmann machine, could be used to efficiently train these deep multi-layered networks with backpropagation.
So it's like they had all these pieces of the puzzle, right? They had those powerful multi-layered networks. They had that feedback mechanism of backpropagation. And now they had a way to make it all work together seamlessly.
Yeah, it was a huge moment in AI.
Yeah.
It really ushered in the era of deep learning.
Yeah.
That's where these multi-layered networks trained with backpropagation, they were suddenly able to tackle these problems that people thought were impossible for machines.
This is where it really does get exciting, right? It's no longer just theoretical. We're talking real-world applications that are totally transforming industries, transforming our lives.
Absolutely. I mean, deep learning is everywhere now.
It's true.
It's powering those voice assistants. It's enabling self-driving cars, revolutionizing how we diagnose diseases,
It's true.
Even helping us understand, the vastness of space. It's amazing.
It's incredible to think that all of this really stems from the work of scientists like, Hopfield and Hinton, who dared to look at the brain not just as, a biological organ, but as a source of inspiration for actually building intelligent machines.
Totally. And they've changed how we understand intelligence,
Yeah.
How we understand learning, the very nature of computation itself.
It's a real testament to the power of curiosity and collaboration and this, this relentless pursuit of knowledge.
Absolutely.
As these technologies continue to evolve, at this crazy pace, it makes you wonder, what new frontiers are out there? What mysteries are we going to unravel next?
That's the question, isn't it?
Well, listeners, we've reached the end of our deep dive into this year's Nobel Prize in Physics. From the early days of artificial neurons to this mind-bending world of Boltzmann machines and the totally transformative power of backpropagation, we've journeyed through the key breakthroughs that have shaped the entire field of AI.
We've seen how physics, neuroscience, computer science, they've all converged to create this technological revolution. Yeah.
And we've only scratched the surface. The world of AI is massive, it's rapidly evolving, and it's full of possibilities and challenges that, we're going to continue to explore in future episodes.
Oh, absolutely. So many more deep dives to come.
Until then, keep those questions coming.
Yeah, don't be afraid to be curious.
And never stop exploring the world with a curious mind. Thanks for joining us on The Deep Dive.